So let's take a look at some of these by example. On this first example, the first time I work it, I'm going to do it by the traditional approach. The second time I work it, I'm going to do it by the alternate approach. So how many liters of oxygen are needed to burn 50 grams of methane? We're going to need a balanced chemical equation. We need to write a formula for methane. It ends in A and E, which tells me it's going to be an alkane. The prefix meth tells me that it has 1 carbon. So to start writing the formula for methane, I've got 1 carbon. To get the number of hydrogens, I take the number of carbons times 2 plus 2. That's going to give me 4 carbons. When it's burning, it's reacting with oxygen. And the general pattern for combustion is that we take all of the elements that are in our fuel, which in this case is carbon and hydrogen, and we're going to turn them into oxides. For carbon, as long as we've got good burning conditions, we're going to get carbon dioxide, and the hydrogen is going to end up as water. We also need to balance this. It looks like the carbons are balanced with 1 carbon on each side. The hydrogens, not so much. We have 4 hydrogens on the left and only 2 on the right. So I'm going to add a 2 out in front of water, which gives me 2 times 2 is 4 hydrogens on the right. That leaves oxygen in water. I have 2 oxygens, the coefficient of 2 times the subscript of 1 on oxygen. So 2 oxygens from water, and then I have 2 oxygens from the carbon dioxide. So 2 plus 2 is 4. So on the on the left-hand side, the reactant side, I need 4, which means I've got to put a coefficient of 2 out in front of there. One little pre-calculation thing I'm going to do, since the problem is talking about grams of methane, at some point I'm going to have to do a mole triangle conversion that involves the molar mass. So I'm just going to pre-calculate the molar mass. So for methane, CH4, the molar mass is going to be 1 times 12.01. That's the contribution from carbon, and the contribution from hydrogen, there are 4 of them. And hydrogen's mass is 1.01. That's going to give us a mass of 16.05 grams. That's the mass of 1 mole of methane. So we have that ready to go when we get there. We're going to start our dimensional analysis by taking the number, the unit, and the chemical and placing that over 1. So 50.0 grams of methane. We need to write all 3 things, number, unit, and chemical. I just want to make this look like a fraction. Sometimes I just don't even bother writing the 1 down below, but yeah, if we want to make that fully a fraction, we'll put a 1 down there. The bottom of the next step has to have the same units as what we were given and the same chemical. So grams of CH4. In the traditional way, this first conversion, the second fraction that I'm writing, is going to convert what we were given into moles. That's the purpose in life. The purpose in life of the second fraction is to convert grams of methane to moles of methane. So when we're converting the units of a chemical, that's going to be a mole triangle conversion. So I'm just going to get the numbers from the mole triangle. The number that goes with grams in the mole triangle is the molar mass. That's what we calculated earlier. It's 16.05. The number on the mole triangle that goes with the word mole is 1. So 16.05 grams for every 1 mole of methane. Our next conversion factor is going to convert moles of methane. So I'm going to start down here with moles of methane. And it's going to convert that to moles of what we're trying to find. We are trying to find oxygen, so it's going to take us to moles of oxygen. This is interpreting the coefficients of the balanced equation in terms of moles. So we have 1 mole of methane for every 2 moles of oxygen. So we just converted chemicals. The last thing we want to do is make sure that the oxygen is in the units we were asked to find. We were asked to find liters of oxygen. So I need to convert moles of oxygen to liters of oxygen. The numbers that we're going to throw in here are strictly from the mole triangle. With moles, we had 1. With liters, we have 22.4. And then it's just a matter of running all of that through a calculator. I'm going to round my answer to 3 sig figs. Typically, when we do dimensional analysis, we treat the conversion factors as exact numbers. In the case of the mole ratio, 1 to 2, that absolutely is true. In case of the others, maybe not so much true. It's not strictly true, but we generally treat them that way. So what that boils down to is figuring out how many significant figures are in the number that we were given. And we were given 50.0. Trailing zeros are significant if the decimal's written, so both of those zeros count as sig figs, and we've got 3 sig figs in our given. So that's going to make me round my answer to 140 liters. To make sure that we're indicating that 0 is a sig fig, I'm going to write the decimal point. So we've got 140 liters of O2, and I got a little sloppy here. I didn't show all my units canceling out. Grams of methane cancel with grams of methane in the next step. Moles of methane cancel on the bottom with moles of methane in the next step. Moles of oxygen cancel with moles of oxygen, leaving us truly with just liters of oxygen for our final answer. Okay, so we end up with 4 fractions are given. The second fraction converts from grams to moles. The third fraction converts from moles of one chemical to moles of another chemical with the coefficients, and the fourth fraction converts the moles that we just found into the units we were asked for, which is liters. We can also do this problem by our alternate method. I'm just going to quickly rewrite some of the stuff we found before. The balanced chemical equation was 1 methane reacts with 2 oxygens to make 1 carbon dioxide and 2 waters. And we found that the molar mass of methane was 16.05 grams. To start this by the alternate approach, we're going to take the number, the unit, and the chemical that we were given. There we go, 50 grams of methane. And our conversion factor is going to have 2 numbers in the top and 2 numbers in the bottom. I always build these from the bottom up to make sure my units are working out okay. So I know the bottom of the next step needs to say grams of methane. We are looking for liters of oxygen, so I'm going to put liters of O2 in the top. The fact that we've got 2 different chemicals here is telling me we've got to put 2 numbers out in front. One of those numbers comes from the mole triangle and it matches the unit. So when you look at the mole triangle, grams has molar mass. So I'm going to put in 16.05. The second number we're going to put in here for this conversion factor is the coefficient from the balanced equation. Methane has a coefficient of 1. The next thing up top, I've got liters of oxygen on the mole triangle. The number that goes with liters is 22.4. And the coefficient on oxygen is a 2. So up top, it's all about oxygen. Down below, it's all about methane. And if you run those numbers through your calculator, you'll notice these are the exact same numbers that we were running in the traditional way of working the problem. And we're going to end up with 140 liters of O2.